Hello everybody. I'm going to make a somewhat longer YouTube video about the analemma and what it shows us about our planet. This was all inspired by Castaway. I'm going to show you just a brief scene from Castaway. This is my darkened classroom. I'm going to hit play here.
Here we are today. It gives us another month and a half until we're into March and April, which is our best chances for the high tides and the offshore breezes. We need 420.
Now, Chuck Nolan, stuck in his cave, has ended up making a figure 8 shape by keeping track of that little spot of sunlight that shines through his cave wall. I talked in class about that's physically not possible for him to have done because he didn't have a way to tell time. Okay, now I'm going to hit pause for a second and turn on my classroom lights and we'll go on. All right, so the movie Castaway inspired me to check into what analemmas are and how our planet does this. Okay, you have to be a nerd or desperate like Chuck was and follow the sun in its position through an entire year to make this shape. Okay, you have to be able to have a way to record where the sun is in the sky, or it's also found it easier to record the shadow the sun is making with a fixed object. You have to be able to watch that sun position or shadow position shift through a whole year by watching it at exactly the same time of day. Okay? Now, later on I'll show you pictures from my classroom PC screen, but here's how I had the exact time of day. This is a shortwave radio. All you can hear right inside here is static from the fluorescent lights and emergency exit lights also make a lot of static noise. When I get out in the locker bay, we should be able to pick up Colorado. Did you hear that change? I don't even have the antenna up. There we go. Just listen. This is the world's most boring radio station. It's called WWV. This is a shortwave radio I made from a kit. This radio station's in Boulder, Colorado.
At the zone, 2 hours, 56 minutes. Coordinated Universal Time.
Okay, sorry it took so long, but okay. So Coordinated Universal Time is the time at the prime meridian. Okay, it's already 2:56 a.m. in London. I'm recording this at about 9:56 here in Albert Lea, 9:56 p.m. Okay, now I'm going back to my classroom. So I use this to have the exact time. And I did this 20 years ago. I took my students out with this radio and a can of spray paint and a metal washer about the size of a quarter. And we would make a mark where the tip of a shadow, I'll show you, the tip of a shadow of a pipe that's out in the parking lot placed to protect the geothermal wells. Okay, now here is the finished project, the product of a year's worth of work, of being a dedicated nerd, okay? The very first Thursday of the school year in 2004, sorry about my hand there. Trying to steady it. We marked the shadow right there, the one that's being pointed at, and then every first clear day of the school week throughout the school year, we marked these. I think there's 43 of these. We had 43 clear days that we marked. This is the winter solstice. It took a year. The gaps you see are cloudy periods. Now, notice here in the summertime, they almost overlap. In fact, they do overlap right here, where, well, I'll explain later, Earth is slower during the summertime. Over here, look at these gaps. Like there's a gap of a week. Okay? The Earth moved a lot during that time. Okay, I'm going to fast forward. Now here to the summertime, look at how little the Earth moved in a week. That was a week. That was a week. Okay? So the Earth is changing its speed during the year. That's one thing. Okay? All right. Now, the phrase I've coined is Earth is an Earth-a-sketch. Almost everybody knows how to play around with an Etch-a-Sketch, and that they know that if you use these two knobs, you can make all kinds of complicated shapes, including curves. Even though the knob only moves the pointer, one knob moves it vertically, the other knob moves it, the pointer, horizontally. But you can make incredible shapes if you move the two knobs at the same time. Okay, you can even make a shape like that, which this is the shape the Earth makes. It has two different motions. All right, these are the notes we took today. Okay, one motion is this, back and forth like this. It takes a year to do one trip and back. It takes a year. That's one motion. The other motion is this one. Takes a year. Back and forth. And if you're weird enough, dedicated enough to pay attention throughout a year, there's 43 dots on this diagram here too. Okay? You can actually watch the world change its speed, and you can watch the sun go back and forth, north and south on the horizon. Okay? Now let me talk about that moving north and south on the horizon. That's caused by Earth's tilt. Okay, I'm going to get rid of this. Escape. All right, let's see. All right, this is one of my favorite websites, Astronomy Picture of the Day. Now, I don't know how well you can see this. This is a picture taken behind a unique skyscraper or something right here. Not skyscraper. Unique building at the December solstice. Okay, you're looking straight east. Look at how the sun is far to the south, to the right, southeast. Okay, in January, the sun has moved a little bit north. In February, it's moved much more north. At the equinox, March, you're looking straight east. Look how much it's sliding. And then April, and then May. Notice the camera hasn't changed a bit. Okay, and then June. Okay, first day of summer. That's as far north as the sun will go. Now it's going to start sliding back. July, August, September, October. Look at how it's sliding back. November, and then back to December. So that was one complete year there. Now watch, I'll do it again. See if you can see it. See the sun slide back? That was 1 year. Now, that motion you just saw explains this. This motion here is caused by the world's tilt, 23.45 degrees. Now, this motion is caused by us changing speeds as we go around the sun. Okay? Our orbit around the sun is not a perfect circle, and the sun isn't in the exact center. So we go slightly faster at one part of the year, in the wintertime. We go faster in the wintertime and slower in the summertime. Okay? The gaps were about more than my hand span in a week up here on the winter end of my analemma. And in the summertime, they were the Earth motion made the sun look like it had moved about an inch. These overlapped. Okay? So here's the weirdest thing. People just don't get it. We're actually closer to the sun in the winter time. About 3% closer. But it makes us speed up because of gravity. As we swoop around the sun, we're actually faster in the winter. And as we're farther from the sun in the summertime, we slow down a little bit. Here's the figure 8 shape. Okay? This is produced by the slide this way, tilt, and this way, changing speed. All right, now let me see if I can show you how I did the analemma some more. This will be the high school parking lot analemma I made. I've done 2 of these as I jostle the phone around. Let's see. Okay. Here is, I've got all kinds of pictures. All right. This is the pole I used. It's about 4 feet tall. It's out in the high school parking lot near the northwest corner. And it's casting a shadow here. You can see it. But this isn't at the right time. As the world turns, it makes the sun look like it's the one doing the moving. It's actually the world doing this. A couple of hours later, this shadow will be over here. Actually, several hours later. Okay? I took this picture in the early morning. And this analemma was made, I think, around 10 o'clock. So anyway, so let me show you a different picture. This is the finished version when I got it all repainted and connected up with sidewalk chalk. Okay. This is the day in September when I got the analemma completed. It's a happy day when you get this year-long project done. You're not tied down to it anymore. Because I couldn't leave town for a year for more than a few days so I wouldn't miss this. When I did go on a fishing trip, I had a trained volunteer who could fill in for me down here on this summer end. Anyway, here's a close-up of the summer end. Look at how little, those are each a week apart. And they actually overlap. Those spots are the size of a quarter. Okay, that's the summer end when our slowed down planet makes the sun look like it isn't moving very much. Here is the winter end. That's a week. Look at the difference. Okay, let me see. This is during the construction. This was the first day of winter. It's Christmas vacation. Nobody's in the parking lot except my truck. And look how long this shadow is. If you had laid down with your head on the ground and you faced this pole and you squinted your eye and you had your eye right there, if you looked back toward this pole, you'd see the sun 93 million miles up that way. Okay? This is the pole and the shadow. That's my shadow. Okay? And if you look very carefully, you can see the faded line of the orange spray paint. Okay? Let me see. Winter end. Oh, we'll go back. Let's see. Yeah, this is another view of the first day of winter and the long shadow. That's about 14 feet long, that shadow, from the base of the pole to there, about 14 feet. All right, now let me show you something else. I was watching the local news, and they were showing a news story about somebody putting solar panels somewhere, and they're using a computer simulation to show how efficient the solar panels would be at this place. Okay, now let me see. I'm gonna back that up and do it again, and I'll loop it. What do you see on the screen? What shape should catch your eye? Look at the analemmas. Okay, let's see if it loops or not. I hope it does. Yep. Okay. So the sun's at its highest in the summertime. The sun's at its lowest in the wintertime. People have to plan out this ahead of time to make sure if they're going to put solar panels that they're not going to have trees blocking their way or tall buildings or whatever. You can have computer simulations run this. It knows where the sun will be in the sky throughout the year. So I just thought, oh, look, analemmas. You can see one just peeking up over this horizon over here and one just over there. Okay. Now, let me show you some different pictures. Let me see. Sorry, I'm going to hit pause. Here, I'm back. Now, if you Google the word analemma, you'll get cool pictures like this. Several people have dedicated themselves to doing this with cameras photographically. This is a camera that had a solar filter on it, and they left the camera in one spot for the whole year, and it looks like they took pictures about once a week. Okay. So you can either photograph the sun in the sky, which is tough. I took the easy way out, and I photographed the shadow that piece of pipe sticking out of the parking lot cast. So here you're looking where the sun is in the sky. I was looking at where it was blocking out light. Okay, let me show you a different picture. Let me see. Oh, where'd the other one go? And this is a cool shot taken over an old temple ruins, I think in Greece. Anyway, so when you see gaps, that's when they had cloudy weather. Okay, it's a nice clear shot. I hit pause. All right, I'm back. Now, here's an analemma on my classroom globe. Okay, I'll zoom in on it a little bit. Look at the inside of it, right? Let me get my hand where you can see where I'm pointing here. Look at the inside of it, okay? Notice the figure eight. I guess it's kind of a tan shape, tan color, okay? That's the analemma. I want you to notice where it is. It stops at the Tropic of Capricorn here, and the Tropic of, sorry, that was the Tropic of Cancer. Go back. That was the Tropic of Cancer, and this is the Tropic of Capricorn, right there, okay? In other words, the analemma is 23.45 degrees wide, okay? That's caused by the 23.45 degree angle that our planet is tilted. That tilt is what makes the north-south slide of the analemma on the Eartha sketch. Okay, that 23 and a little bit, it's almost 23.5 degree angle. Okay.